Hello, I'm Julian. I work for Datadog and I started the Parquet project. And today I'm happy to have a chat with Julian Hyde, who is going to talk about Morel, his new language, query language, in comparison to SQL. So Julian, go ahead.
Thank you. It's good to have two Julians on the call. Hope it doesn't get too confusing, but yeah. So I'm going to reprise a presentation I gave last week at Data Council in Oakland, and hopefully this will be an interesting conversation.
It should be.
So yeah, I'm going to be talking about Morel, which is a functional programming language that also does query. And I'm going to talk about some of the differences and similarities between query languages and programming languages. And using Morel as an example, but also plenty of examples from SQL and some other query languages. So really, I'm exploring what we could possibly expect from a query language if we make it more similar to a programming language. So to start off, I want to kind of ground the conversation. I want to look at a problem that you really wouldn't want to solve in a query language, but just look how it just take a look at the solution in Morel and just examine how the solution turns out. So I think most of us have played Wordle at some point, and figuring out what word to guess next is a hard problem for humans, but it's also a hard problem for computers. It's not a small problem because there's 13,000 possible words, and in some sense it's a kind of an optimization problem, so choosing the best word to guess next. So I actually played Wordle last week. This was based on the actual problem a few days ago. And I get Aster as the first word, and the two yellow squares indicate that the letters A and R are in the word somewhere. And for my, there's several words I could guess next. And let's suppose I could choose the word wharf or the word moral. If I choose the word wharf, then we can see I could get various solutions back. I could get various answers back, various colorings of the letters. And it turns out that if the coloring comes back as black, black, yellow, green, black, then there are 50, 60 possible words that could be. Whereas if I guess moral and I get the same answer, then there's basically 7 possible words that could be. So if you compare those two possible choices, wharf is a less good choice than moral, because moral generates 49 possible groups of words, and therefore whatever answer I'm getting back, I'm getting more information. It's narrowing down the search space more. So I wanted to encode this as an algorithm. So for each possible guess, you look at all the possible answers, and you compute the mask, which is the set of colors, such as black, black, yellow, green, black, for each of those answers. And you look at the number of distinct masks that you can get. And the idea is a guess that produces a lot of distinct masks. In the case of moral, it produces 49 distinct, is a better answer. So I actually coded this up in the Morel language, and ran it, and you can see in kind of line 4 the word moral occurs with a mask count of 49, and the word wharf occurs way down because it's less popular. So essentially, what it's recommending is the best words to choose next. And ironically, I mean, Morel was one of the guesses, and I said, well, let's go with Morel. And ironically, it turned out to be the correct answer, which is kind of not perfect for this pedagogical example, but there it is. So what's more interesting to me is how you actually write the code. And this is basically, it turned into 2 small pages of code. And this is the first page. And as you might expect, these are a couple of functions in the Morel language. And they're all basically messing around with how to convert lists of colors into integers that we can use as keys. And so they're picking apart the letters, strings into the individual letters. And this is pretty typical of a programming problem. You just spend, a certain amount of time preparing your inputs. And this is something SQL is not very good at, because, most dialects of SQL, you can't define user-defined functions in SQL. You have to go into another language for them. And certainly if you need to do iteration and recursion, you're out of luck. Then the second half of the problem, well, the first line is basically just reading a table of words from the file system. So kind of like data frame languages, you can just convert a file in the file system into a relation. And now we define three functions: mask, count, best guesses, and remaining, which if you look inside them, I know you don't know the Morel query language, but you can see, from and group, and order and where. And so you can see that these things basically look like queries. So we're working on this collection of words and basically executing queries on these things. And it turns out that and this is the whole, these 2 pages of code, this is the entire solution. It turns out that, kind of contrary to our expectations, the solution is actually doing a kind of query. And that means it's the kind of thing that if we have a efficient query engine like DuckDB running locally, or Spark running on a distributed Spark cluster, it turns out this is a very good way of solving a kind of data parallel problem. And because it gave us a little more power than SQL, we were actually able to solve the whole problem and end up with something which actually in structure kind of looks similar to a SQL query. All right, I hope that makes sense. I'm trying to motivate this idea that the difference between a programming language and a query language is actually not that great. It's just a query language. You can't solve real problems because sometimes you need a little bit of extra power that isn't in a query language. So yeah, today we're going to be talking about what is the difference, or is there a difference between query languages and programming languages. Talk about things in SQL that can be improved, and then introduce Morel. So I'm using the word algebra, and relational algebra. Well, what do we mean by algebra? Well, mathematically, an algebra is a collection of values and operations on those values and laws on those operations. So, if we're doing algebra on, arithmetic, we know that a plus b plus c gives you the same answer regardless of which order you do the numbers. And we also know by De Morgan's laws, a times b plus a times c is equivalent to a times b plus c. And if the values happen to be relations, in other words, sets of records, there are similar algebraic operations like union and join, and they actually have similar looking laws. Now, the laws are not identical, but those laws are what a query optimizer takes advantage of when it's basically trying to take a query that you've written in SQL or another relational language, and is trying to convert it to something that's more efficient and perhaps takes advantage of the partitioning of the tables, or the fact that the data is in sorted order, therefore it can evaluate joins more efficiently. So if our language has an algebraic structure then this is huge advantage in terms of being able to optimize the programs and execute them efficiently. In contrast, functional programming, there are no built-in operators, but they have algebraic capabilities to them. So this is a piece of some various examples of expressions in the Morel language. This would also work in standard ML and probably OCaml, which are just related languages. So we've got integers as a list, and we've defined a function called filter recursively that applies a function, takes a list, applies a function to that list, and returns all the members of the list where the function evaluates to true. So we can do this, we can take the integers and we can filter out the even integers by applying this function. So if we look at relational algebra and functional programming, well, relational algebra has the set of operations like union, minus, intersect, and join, and so forth. In a functional programming language, we can actually just write functions for all those relational operators. It's not very difficult to do. So why isn't this the solution to the problem? Well, the problem is that in order to evaluate these programs efficiently, the system actually has to understand these relational operators and the laws that apply to them. So it's not enough for the functional programming environment to just evaluate union and then evaluate filter. You actually want it to perhaps push the filter through the union, apply these algebraic transformations. So by bringing the languages closer together, there's an opportunity to produce something that's better than both. So is SQL a functional programming language? It's an interesting question to ask. I'm not really sure whether it is or it isn't, but let's just dive into this problem a little bit. So a functional language, as we said, has got you defined the operators yourself, you can define types yourself, you're allowed functions as values in addition to all the other kinds of values like lists and integers and records and so forth. The optimizations that happen are all local. In other words, they affect small regions of the program, but they don't affect the whole structure of the program. And functional programming languages are, most of them are Turing complete, meaning you can compute pretty much anything. And they execute locally, not on a cluster of a distributed compute. Query languages, the operators are a much smaller set. They're built in. They're the relational operators, and the only bulk data type is relations. So you can have things like lists inside the columns of that relation, but if you have a gigabyte of data or a terabyte of data, that's going to have to be residing in tables. It does algebraic rewrite, which is, as we've said, a better operation, especially when you've got large amounts of data. But it's not Turing complete, and it's just practically not complete enough to solve problems such as Wordle, where you need to pick apart strings and do that kind of stuff. And then most query languages, or let's say some query languages, have a distributed engine. Certainly all the Cloud SQL engines have distributed compute. So what they have in common, and I think these are reasons that people have just instinctively liked SQL from day one, is it treats the data as immutable, which means that it's easy to reason about. When you execute a query, there's no way it can possibly modify the contents of the table. And therefore, two people executing queries can execute those in parallel without interfering with each other. Another thing query languages do is they do type inference. When you write a SQL program, there's very few type declarations. It just figures out the type of all of your values, and if you have a derived expression like x plus y, it can figure out the type of that as well. And it does inlining, which means if I reference a view or a function, an expression defined in a subselect, the optimizer is extremely good basically flattening out the algebra and pruning columns that are not used. And this is something that functional programming languages do as well. So I just want to kind of hint at this, this possibility of a language which is the superset of this, that has all of the flexibility of a functional programming language, including being able to define your own operators. But it has the efficient execution and efficient rewrite capabilities of a query language. And not limited to, there are other bulk data types we would like to implement, like matrices and vectors and geospatial types like regions and line segments and so forth. So all those things have algebraic operations and would benefit from being processed by a data parallel engine. So that's the kind of direction we're heading in with Morel. This is, it's early days yet, but the first step is to, bring relational algebra and functional programming together. So is that making sense, Julian? Any thoughts or questions at this point?
Yes, I'm interested in what user-defined operators will look like. Right, I think that opens up a lot of opportunities. I'm glad we are solving the hard problem of computer science with Wordle.
Yep.
That's
one hard problem at a time. Yeah.
That's a fun problem to pick for the presentation. Yes. Yeah. So I'm looking forward to see. I guess the next step in the presentation is to dive into Morel itself, right?
Yeah. So the user-defined operators are, in SQL, the best we can do is table functions, a function that reads a table, or, a set of rows and returns a set of rows. That's limited in SQL because you might define this table function, but you can't define the algebraic identities on this. In other words, for example, when it's safe to push a filter through this table function, there's just no way of telling a SQL engine what to do that. Mm-hmm. So in a functional programming language, a user-defined operator is just a function, right? And if you define a function that takes a list as an argument and returns a list, well, you've defined a new relational operator, right? So we don't tend to give it this fancy name, but it's pretty easy to define that kind of function in a functional programming language.
But they also don't have optimizer rules that go with them, right? So that's
right.
Interesting to see how those two things come together.
Yeah, and related to operators, they're not relational operators as such, but it's also nice to be able to define your own aggregate functions. Let's suppose you're using a SQL engine that doesn't have a median function. You can implement median by building a set, sorting the set, and taking the middle value of the sorted list, right? So Morel does make it possible to define your own operators like that. And then if you define your own types, let's suppose you define a matrix type, then operations on that might be kind of, inverse and multiply of matrices. And then you can tell it the algebraic properties that, if you want to multiply two matrices and then invert them, that's equivalent to inverting the matrices and then multiplying them in reverse order, right? So you can tell the system about, well, this isn't possible in current Morel, but this is where we want to go. Mm-hmm. Okay, so another way of looking at the same thing is consider the kind of the universe of all of these possible data computations. And you can think of each of these naturally has a particular database that supports it and a particular query language or language that supports it. And SQL is only covering a pretty small part of this universe. So transaction processing, CRUD operations, insert, update, delete, single record retrieval, reporting where you're basically doing joins and adding up numbers. And SQL deals with analytics somewhat, but people also have BI tools on top of their SQL engines because SQL doesn't do everything you might want in analytics. SQL is definitely a part of data engineering, but doesn't solve the whole problem because you kind of need to organize your SQL script into batch jobs and restart the batch jobs if they fail and do conditional execution and so forth. And certainly general purpose programming is way outside of SQL's capabilities. And even things like graph processing, geospatial processing, vector operations are beyond SQL's capabilities. And so with Morel, we're trying to basically broaden the reach of our query language or programming language to more of these areas. So I'm kind of, the expression goes, if you come with a king, you better not miss, right? So SQL tends to win, right? SQL has been under attack for many years, and it's still come out on top. So why do I have the hubris to try and attack SQL? I don't think SQL is going to come to an end suddenly, but I do think that over time it will fade away. I think several different things are going to happen all at the same time. So SQL is going to continue to grow. There's a lot of people just making really useful changes to SQL almost on a daily basis. I mean, for example, last year, Google introduced the pipe syntax to SQL, and vendors are adopting it. But SQL is becoming a larger and larger language, and there were mistakes made in the early days of the design of SQL that we have to live with. I'll mention one or two of those later on. The ISO standard seems to decline in importance, and this kind of standard, industry standard SQL seems to be more defined by particular vendors coming up with a good idea and then their competitors adopting it, which means that standard SQL is becoming less organized, but still growing. So I think the way SQL will decline is we'll have databases that can actually speak more than one language, so polyglot systems. So you have a system that speaks SQL, but also perhaps in future it also speaks Morel as an alternative language, and perhaps it's speaks a language like Sparkle. So there's no contradiction there if that database has a common set of data objects that can be addressed using multiple languages, and you're still the same computations are happening regardless of which language you use. I think that's a nice scenario for end users. And the benefits of having central definitions of your data and centralized access control are still pretty significant. Another pattern that I see is people putting layers on top of SQL. So if you're using a semantic layer or a BI tool, there's still SQL under the covers, but it's not written by humans. And so SQL is still there, but it's less important. It becomes kind of more like the machine code of the system. And certainly, we're seeing natural language query is improving over the last few years, and so those systems are going to be generating SQL, but most users are not going to be writing SQL themselves. So if AI is going to be generating queries, there's a case for us having a better query language than SQL, and therefore maybe that's going to improve the capabilities of natural language query faster, because Morel or something like it is an easier language for the AI to generate than SQL, perhaps. So let's look at all of the other languages out there. There are a lot of languages out there that are not SQL. So I'm not going to go into these in any detail, but these examples are all generated by, I asked Claude to translate a SQL query into various languages. And as you can see, the syntax has a large amount of variation. Here's some more, including xquery and link. There's a large amount of variation in the syntax, but if you understand the language, you can see the same relational operations are happening in all of these languages. All of these languages are based on relational algebra. And the syntax of the language really just tends to reflect the client, in other words, the people and also the environment they're working. So, for example, XQuery, because it's designed to be in an XML environment, then the query language basically includes large amounts of XML. So actually, there's less difference between these languages than you might think at first, but they're just customized for the particular environment and the particular workload that people are using it for. I'm pleased to say, you know, Morel here is concise and in fact looks pretty similar to the SQL. I mean, conciseness in a language is a good thing, and it means that you're doing kind of a lot of the things right. It's not everything, but it's a desirable trait and something we've definitely designed for in Morel. Okay, so let's look at let's just drill in more detail to SQL and other related languages. So here's a SQL query that's querying a table of sales of produce and then aggregating it. And as we mentioned earlier, one of the innovations in the SQL world is Google SQL pipe syntax, which is now being adopted by other vendors. So the interesting thing about Google SQL pipe syntax is it is actually still SQL. It's still handled by exactly the same SQL parser. The type system is the same. The expressions have the same syntax. And it is an improvement just because the query is ordered in the way people think and in the direction of the flow of the data. So everyone that knows SQL knows that the data starts in the produce sales table in the from clause. And so Google SQL Pipes is just fixing this initial mistake and putting the from clause first, which means that as you extend your query and feed it through more steps in the pipeline, you're going to be just adding extra lines onto the end of the code. And it's a little bit more concise than the original SQL because you don't have to repeat yourself, repeat the group by clause. So the aggregate operation is implicitly saying, I want you to omit item. So Google SQL is definitely an improvement, but it's an evolutionary improvement by people that basically want to stay in the SQL world. There's another language that's been getting a lot of acclaim and interest. It's called Prequel, PRQL. I think they were earlier than Google SQL Pipes in putting the from clause first. But you can see these same set of relational operations, with filter and group and sort are really these relational operations. And it's, nice and concise. And then lastly, Morel, which again has this from keyword first. It uses the where clause inherited from SQL. So we wanted to make it easy to learn for people from SQL, and therefore we used the SQL words when they made sense. Now, we didn't use the word select because select, select means it means filter if you're doing academic relational algebra. So we actually used the word yield rather than the word select. But other than that, as you can see, it's pretty similar to SQL.
So I had a question. Why are you using, I'm sure there's a good reason you're using and also as a keyword here instead of and. So what's the reason for that?
Yeah, it's not a super good reason actually. But Morel, when we were building Morel, we started off with an existing functional programming language, standard ML, which had an elegant syntax and has an elegant type system. And we really wanted to start off with something that was, pretty much complete in terms of being, powerful enough to solve general purpose problems and had that nice type system. And standard ML, for various reasons, it used and for something else. So, and in fact, and is used for simultaneous declarations. If you want to define mutually recursive functions, then you use the and keyword so you can declare both functions simultaneously. Now, I think Boolean and is much more common than wanting to do kind of simultaneous declarations. So this is a case where we really should evolve the syntax of Morel away from standard ML towards something more useful. And so that's one of those areas that I think we probably should change. And I guess people will differ whether we should use ampersand like Java and C, or whether we should use and like SQL. I'm not sure. But there are definitely places that Morel syntax can be improved, and I expect to evolve it some over. We're not at 1.0 yet. I expect us to evolve it as we get just feedback on the usability of the language. I think syntax changes are something we should be doing.
Sounds good.
And yeah, so this is not the full syntax of Morel, but this is the syntax of queries in Morel. So on the right-hand side, you can see a list of the various steps. Now, a few of those are not implemented yet. We're releasing Morel version 6 this week, hopefully. And that includes a couple of extra steps, but these are things we hope to have ready in the next couple of for example, union, intersect, accept steps are something we hope to have in the next month or so. The yield many step again is not yet implemented.
Is yield many like a flat map? Is that?
Yeah. So I am still trying to decide whether yield many, yield all, flat map. I think if we called, I think if we could, of course, rename yield to just map, and all the functional programmers would go, I understand what that means, and all the SQL programmers are going, what the heck does map mean?
I mean, yield many is intuitive enough, right? Like I kind of associated it to yield makes sense, right? Like you can use yield in Python, for example, when you have a generator function.
Yep.
To which I think this relates very well.
Yep.
So I don't know, yield many feels relatively intuitive.
Okay, good. That's good. That's good feedback. Yes.
Flat map, so the first time I learned functional programming language, flat map was not intuitive to me.
Right, absolutely. It's not intuitive, and then you learn it, and now you see a language without flat map, and you go, "Where's flat map?" Right? Yeah. So yeah, a general Morel queries generally starts with this word from. In other words, a query that's going to read some data sets and produce, say, a list of records. But we've also got a couple of kinds of query called exists and for all. So these are existential quantifications. So if I want to run a query just to find out whether it produces any rows, I can use I can replace it from with exists, and therefore the yield doesn't actually matter, right?
Mm-hmm.
I'm just interested, does it produce any rows? And then for all is a similar thing. I'm interested in, does a particular Boolean expression evaluate to the same thing for all rows, or does it evaluate to true for all rows in the query? And that for all query, the last step has to be this thing called require. Anyway, we're mainly going to be talking about from these days in this talk. So jump into some more examples now. So this is I guess my favorite example of the thing that was done wrong in SQL, and done wrong in quite a few programming languages. Do you have any idea what the $1 billion mistake is?
I've heard about null a few times. Yes.
Exactly. Yeah. So here's an example of where you're being bitten by null and you don't even think you're using null. So I'm interested in saying, find all employees in department 10 that earn more than all the programmers in department 20, right? And I run this query, and I'm very surprised to find that it's outputting all of the employees in Department 10. And the reason is that there are no programmers in Department 20. And what happens if there are no programmers in Department 20? Well, that subquery is going to return no rows. And max applied to no rows returns null. And I'm sorry, it doesn't return all the rows in Department 10, it returns no rows, right? So, salary greater than null evaluates to unknown, and therefore there are no records returned. And you would think, I mean, logically, you would just expect if there are no programmers in Department 20, then trivially, all employees in Department 10 earn more than all the employees in Department 20. But null has just messed things up, and it's just snuck in there because of the way SQL deals with aggregations over an empty set. And it's just caused you to spend 2 hours debugging something that should have been simple. So
to get the correct answer, you would have to use a coalesce function there, right? To say, and have input a default value. So it's a case of the default behavior is swallow the errors, right? It's kind of this, and the null in SQL is it contaminates everything, right? Like, because anything operation with null returns null, right? So it's kind of everything's false, and it just like contaminates your operations. And so it's by default, when we don't know what to do, we just skip the rows, right? Which is kind of a bad default, right? So you can handle this, but you need to make it explicit, right? Instead, the default behavior is just ignore the errors and drop the rows, right?
Yep.
Which is, I guess, bad. As a programmer, I don't like, I like when things fail fast rather than default to dropping things.
Yeah, I totally agree. Yeah, it's just bad design, right? Something that, if you've got an electric can opener in your kitchen and it does the right thing, 80% of the time and cuts your thumb off 20% of the time, that's bad design, right?
Well, I have 2 thumbs, right?
That's right. That's a mistake you'll only make once, right? Yeah. So, why did they put null into SQL? Well, there are various reasons, right? Empty strings was one reason, not a particularly good reason, but missing references like employees that don't belong to a department or whatever, employees that don't have a manager. You can see there's a need for that, right? Missing values, like suppose someone has just not entered their social security number in yet, right? You need to represent this data. And then there's the unknown Boolean value, which I think is the worst use of null, which is to say it's true or false or unknown. And if I say, for example, x greater than y and y is null, that will evaluate to unknown, and this is where this contamination happens. Also, aggregation over the empty set. There are cases where we want aggregate functions, and that they apply to a set that is empty. They obviously have to return some value. So there are all these various reasons that require null, or all these problems that have to be solved in SQL, and null seem to be the solution to all of them. I just claim that it's not a good solution to any of them. I mean, for empty strings, just use an empty string, right? Functional programming languages, actually a lot of modern programming languages would just use an option type. So for anything that, a value that could be missing. And Morel does the same. And I think the unknown Boolean is just, it's completely unnecessary. If you actually want to do reasoning about, Booleans which are true or false or unknown, you can use that option type. But most of us, most of the time, actually are just interested in true or false. And as we'll see, aggregate functions, it just makes sense when you define an aggregate function that you're forced to say what the value should be if the set is empty. Or perhaps you have another variant of the aggregate function that just returns an option, and therefore, if the set is empty, it just returns, none, which is the, the empty option. So back to that's this original query. Let's look at how we solve it in Morel. You can use this for all construct, where I'm kind of saying literally what I mean. For all, find employees in Department 10 that such that for all employees, all programmers in Department 20, the employee in Department 10 has a higher salary. Or you could do it a different way, and you could say the salary is greater than the maximum salary in Department 20. But here we've got compute max 0 of E2 sal. So max 0 is saying we're using the max aggregate function, but we're giving an extra argument to say it's max that if the set is empty, it should return 0. So that gives us the desired effect. And if I call max with only one argument, the list of salaries, it's going to give me a type error saying you haven't given me enough parameters for the max function. So I hope you'd agree that this is, the language is basically just forcing me to do the right thing and is raising questions if I, forget to deal with the case where, the set of programmers is empty.
Yeah, that makes sense to me. I mean, it's interesting. Like the thing is, this whole thing about having to define the default return for max when there's no entries, it's even something that's not there. You don't actually care about the max, right? You want the for all operator, and because it's not there, you have to do max, and because it doesn't force you to define a default, then you end up with this weird behavior where you didn't even need to compute the max to start with. You just wanted all of them. It's just SQL,
Yep.
You return something, right? So you can do that. So yep. It's interesting to have this for all operator. That makes sense.
Yeah, and there's also this theory that I really subscribe to, which is when you're writing a program, you're communicating not with the computer, you're communicating with the person that's going to maintain your code.
Mm-hmm.
So I would just write it in whichever way just makes it most obvious what's happening.
Yeah.
And then you trust the query optimizer to produce the same plan for both of those variants of the program.
Yes.
Okay, so let's just dive into types, which is types are central to functional programming languages, and we're going to want to think about types because I claim that the world is not all relations, and when you're doing general purpose programming, you do want a richer set of, especially a richer set of collection types. So just briefly, a programming language has primitive types, the built-in types like Boolean and integer and floating point, and then abstract types that you can define for yourself, that like interval and point and complex number that act as atomic types, and then there are collection types, and as I said in SQL, in academic SQL relations are sets, but in industrial SQL they're actually bags or multi-sets. In other words, they're not ordered, but you are allowed to have duplicate values. But for a lot of real-world programming problems, lists, you want ordered collections. Functional programming, all the way back to Lisp, the list processing language, they operated on lists. And so for an awful lot of real-world problems, you do actually want to operate on ordered collections, i.e. lists. Functional programming languages have polymorphism and function types that are definitely not even thinkable in SQL. And then algebraic types, which is a fancy way of saying record types and sum types. So a record, called a struct in many languages, or a class in other languages. You've got several named fields, and then sum types, which are they're called tagged unions, which is you've got a particular value can either be an A or a B, right? If you've got a tree, the nodes of the tree could be a leaf which has no children, or it could be a node that has one or two children. So a sum type allows you to represent those different options. And put these together, and now you've got a kind of a way of representing data sets that are, let's say, equivalent power to, let's say, the JSON data model, and you can handle real-world data sets without forcing them. You're forcing everything to look like a flat relation. So here's an example of some of the data values you can define in Morel or indeed standard ML, and you can see you've got I've defined a type, member, which is a record type. Members is a list of employees, and each employee, every employee has a name and a department number, but they might be either an employee, in which case they just have an employee number, or they might be a contractor, in which case they have a social security number and an agency. Departments is one of the lovely things about Morel is it makes no distinction between external tables and local variables. So departments, Scott.depths is an external table in some JDBC database, but I can pull it into departments, which just looks like a local variable, and that local variable looks like a list of records. And in Morel, you can freely join external tables to local arrays and so forth. Then lastly, the bands is an example of the thing where it is a list of lists. So you can nest these data types as much as you want. We had this challenge that I'm actually still working on, and it's not going to make it into Morel 0.6, hopefully 0.7, which is how to reconcile the fact that some data looks like lists and some data looks like bags or multisets, because data coming from tables is going to look like a bag, it's unordered, whereas most data locally is going to look like a list. So what I'm working on is this idea that you can, when you're writing a query, you can actually combine data sets that are lists and data sets that are bags. And there's a way of, if all of the inputs are lists, then the output becomes a list, because if all of your collections are ordered, you want deterministic order on the output. This is kind of similar to how you'd write a nested for loop in a language like Python or Java. But if you really want to go to unordered, then there's a special keyword that converts that to unordered. You'll get the same results, but there's no ordering to it. So, and of course, order is a way to convert anything that's ordered or unordered into something that has a particular ordering. So this is useful functionality that I believe is necessary, because we do a lot of processing on ordered collections.
So that enables the optimizer to make good decisions, because it knows like data has a certain order. Well, you said like tables provide bags unless they've been stored ordered, and then there's some metadata that in the table that give you this information, right? And then you could take advantage of it.
Yeah, that's a good question. In SQL, all tables are officially unordered, but I guess we've got table catalogs. I guess Iceberg is an example of this. I think you know more about Iceberg than me, but you could probably in Iceberg define a table that has an ordering to it.
I think especially in OLAP, right? This is a common optimization that the table is sorted, ordered in some way. Right? So of course, depending on how you access it, if you read it in parallel, right? Depending how you treat it, it can become unordered. But you can decide to maintain the order as you filtering through it and so on, and take advantage of it in the optimization step.
Yeah, ordering is it's a paradox that if you have this table, which is a modern table and a object store or whatever is stored in parallel, right? The table is thousands or millions of files, and so if you're processing it, you definitely don't want to read it in order, because that means you have a parallelism of one, right? But you can still execute an ordered query on it that basically you want to use the ordered operations, an ordered union operation, an ordered join operation, and produce the results, respecting the order. And the system might be smart enough to evaluate that in parallel, even though you're using, the ordered, the information, the extra few bits of information that come from the ordering. And of course, if the query is genuinely unordered, an optimizer, if you execute a query on 2 ordered collections and then follow it with an order by clause, the system should say, hey, they don't actually want ordered processing because they're going to sort it at the end. So the fact that they don't care about the ordering, that should just propagate all the way up through the query plan, and the optimizer should just say, hey, just use unordered semantics for this entire query until the order by clause. So here are a few examples. The top one, we're basically joining 3 lists together. Lists are ordered, and therefore just similar to the way a for loop would work. The output of these, you're just going to get a Cartesian product of these 3 collections, and it's going to output in deterministic order. 1A3 is going to be the first row that comes out, right? The next one, we're joining an array of integers, department numbers, to a multi-set of employees coming from an external table. So because one of those is a list, and the other one is a multi-set or a bag, then the output is going to be a bag. And by the way, also notice that we're only retrieving 1 column. So unlike SQL, we're not actually returning a multi-set of records, we're returning a multi-set of strings. So Morel has just gotten rid of the record structure because, hey, we're just dealing with strings. So this just makes it more concise because we don't have to worry about a field name for this thing. Then the last example, it starts off the same as the previous one, a list and a multi-set, but because there's an order by clause in the middle, and the order by clause allows us to do take, which is kind of like the fetch, fetch the first 3 rows. We're finding the 3 employees with the highest salary. So we do want ordered semantics there. We do get a list as its output, but the join and the early parts of the query can be done on unordered data.
Oh, so can you come back to the previous one? Okay, from that, okay, yeah. So in that case, you keep you do yield explicitly those things, and they're named after the fields. Okay.
Yeah. So when I write e.depthno, kind of similar to SQL, it derives a field name is going to be depthno from e.depthno. That's a small extension to standard ML syntax. And standard ML records, you have to name each field explicitly. But yeah, we wanted to make it look as much like a select clause as possible.
Yeah, and the first one, when you join IJK together and they contain their scalars inside of them, right? They're not they're not records. And then they automatically named after the relations they're coming from.
Yeah, so each of those, I call them scans, the kind of variable in collection. Each scan basically produces 1 new variable that in SQL you probably call a table alias or something. So because you've got 3 scans now, you've got 3 variables, I, J, and K, and therefore because there's multiple of them, implicitly, it's implicitly written yield I, J, K.
Okay. So if let's say IJK contained records, would the 3 top level would have 3 columns, each of them would be a record, or would that flatten them? Like it would be more like a co-group in Pig.
Yeah, exactly. You mentioned co-group, harking back to the days of Pig, right? So, yeah. So yes, they will remain as records. So that includes in the second query, well, you can see we've got E and Scott.emps, right? So E remains as a record value. And therefore, if I want to find the department number field of that record, I have to say E.depthno. If I wrote just where depthno equals dept, that would be invalid. I have to prefix it with the field name. So yeah, Morel tends to keep things as records. There is no select star. There's no simple way of just flattening these things out. It keeps things as records, which I think it's convenient. But anyway, yeah.
Yeah, Pig used to overload the flatten function to do both, right? You could either flatten a bag and it would turn into rows, or flatten a tuple, or like I guess the record, and it would take one level down.
Yep.
Everything in the records, which was a bit like confusing because those are two very different operations.
Yep.
And it used the same function to do both.
Yeah. So yeah, I mean, Pig was a fairly simple and effective relational language, and so this is bringing back, some of the good things that were in Pig. The one thing that I didn't like about Pig was, in order to do a join, you had to co-group. You had to make these multi-sets, right? In order to join employees and departments, you'd have to group all of you have to create this bag of all the employees in the department. So I think that was a vestige of the MapReduce engine, and the fact that, the Hadoop MapReduce engine that didn't actually have a join operation. All it had was shuffles. So that aspect of Pig is long gone, thankfully. It doesn't occur Morel has a native join operation.
Yeah. Pig then had the join operator as well.
Oh, okay.
Yeah, that would so basically it would do the same thing as co-group and then do the cross product between the two co-groups. Right?
Love it. Well, maybe someone will write a Pig to Morel converter at some point.
We could, yeah.
Okay, so let's look at another aspect of, I guess, SQL, how SQL works, and look at how the same problem, comes out in Morel. So I've been working on Morel for quite a while, and my brother said to me, my brother works in, analytics and data engineering, and he said, so what is Morel's DML syntax? And I said, I don't know, but it's probably going to be insert, update, delete. And it really just got me thinking. So let's just look at a simple example of a script. You can think of this as a batch job. It's kind of similar to the kind of stuff you do in DBT. So just illustrating the DML operations. So first of all, we delete all employees who have a salary greater than 1,000. Then after that, we insert one employee. And lastly, we update the table. So we double the salary of all managers, and then we commit. So my first attempt to add this to Morel was to add, insert, update, delete keywords. And what I noticed was I'm kind of replicating a lot of parts of the query syntax, right? Delete, where, and then I had to, figure out this new assign operation to modify the current row in the update statement. And it just seemed to me that it wasn't really building on the query capabilities in Morel. And it was also doing something that is just a bad idea in a functional programming language, which is modifying your data. Functional programming languages work better when you...
Side effects.
Yeah, side effects, exactly. And so this beautiful thing about SQL, immutable data, the DML language, I guess it's obvious to do DML, you obviously have to modify data at some point. But I think SQL is not doing it in the way a functional programming language would. So here's my second attempt that I think is much better. So rather than doing an insert, rather than doing a delete, we can just assign. We can read from the employees table, and we can just assign to a new value, which is the employees without the employees that have a salary greater than 1,000. So we haven't deleted yet, but we've made this new collection, and this collection can be virtual. In other words, this thing could be not materialized in memory, but just could be something that's in the query optimizer's mind and in the internal state of the database, which is what we want the new table to be. And then we follow it with the insert statement. And now we're actually building on the previous employees, right? We're inserting into this table that previously we've deleted from. So now emps3 is defined in terms of emps2, and insert just becomes a union operation. So we've not actually invented any new syntax at this point. This is all just existing Morel stuff. So to double the salary of all managers, it's a little bit more complex, but we're just doing a conditional yield, and that we're reading emps3 this time. And if they're a manager, we yield the employee record, but with the salary doubled. And we use this, I brought this with operator from OCaml as a way of copying all fields of a record, but just modifying the value of one of the fields of the record. And if they're not a manager, we return the record unchanged. So this is achieved the same effect as the update statement. Now, lastly, commit, we actually have to do this mutation, and this is the only new thing there. And what we're actually doing is saying we're writing. So Scott is an entire database. So you can think of this record that contains several fields, one of which is called emps, another one's called depths, and maybe there's 57 other tables. But what we're doing is we're saying take the Scott database value and write it, but change the value of the employees table to be employees for. So write all of these changes that I've just calculated, write this atomically to the Scott database. Now I actually, this example doesn't modify the departments table, but it could, right? We could have a batch job that modifies multiple tables, and then we can use this commit statement to write back all of those tables simultaneously. There's one, besides the fact that we were able to reuse the query syntax of Morel, one very nice effect is that now, unlike SQL, I can actually reference all of the previous versions or all of the previous snapshots of the employees table. So when I'm deriving emps4, I could actually, calculate the difference between emps2 and emps3. So I can access precisely which records would change between the various steps. In SQL, if I reference the emps table in an update statement, it has to be one and only one thing, which is the state of the emps table directly before that update statement. There's no way of saying, what's the committed value of the employees table, for example. That's just not available in SQL. So this seemed to be a really nice feature and really an unexpected side effect that allows me to do very kind of fine, very powerful data engineering by finding the deltas between these things.
Yeah, it's very interesting, right, in terms of how that, because then it's an optimizer problem to not duplicate all the data that doesn't need to be duplicated. For example, if I think, let's say I implement this on top of Iceberg, in the first one, you can just generate a delete vector, create a new snapshot. You didn't touch anything, right? The second one, you just create a file that contains that one row you added, right? And the next snapshot is just all the files from the previous snapshot plus that one file. And so you have all the snapshots. It's very easy for the optimizer to just, figure out what the plan looks like by building on top of the previous version and doing the next thing, right? And for modifying things, it gets a little more complicated because, you have to figure out the files that have been touched, but you can rewrite only the files that contain data that needed to change, right? And everything else stays the same, and you can just have pointers to it, right? So depending on the internal representation of that database, the optimizer can take steps to do that. And I really like the functional view of this, right? As opposed, like when you derive from immutable data structures or collections rather than mutating them, right? And no side effects. And I think it's all really nice. Yeah.
Yeah. Well, yeah. Thank you. I was, you're more of an expert on like table formats than I am, but that was exactly what I was aiming for. And I feel like this is on one hand a higher level language, but on the other hand it's closer to the metal, and it's closer to what the system is actually doing, which is working on, yeah, as you say, when you do an insert, it's actually creating a bunch of multiple extra files that are going to be, when we commit, are going to become part of this table, right? So yeah, and when I say, well, in fact, the next slide addresses this. So if I've said what are the employees added and the employees removed, I can just do an except, a minus query. And this, in the optimizer's mind, this is actually just evaluates to a set of files, right? That are going to be that are the deltas to the table. So emps added and emps removed is actually something that's very efficient for the optimizer to create, because it actually knows what that set of files is. So yeah, we're in violent agreement here, and I think it's going to be exciting to see how this kind of meets the real world of iceberg tables and data lakes and so forth. Yeah, how I think I'm just saying what you already said. How do we optimize these data intensive programs? We efficiently compute deltas. The optimizer is able to do that. But there's some, by putting these scripts of multiple statements into a single query, as it were, a single program, it now actually gives the optimizer to this ability to optimize the entire program. So what are some optimizations you could do in a DML script like this one? Well, you could add materialized views if a particular data set is used more than once in the script. It could actually suggest create a temporary table for those intermediate results. Or if the temporary table is being created that isn't actually being used, it can remove it. And this is in addition to all of the usual things that query optimizers do, like reordering joins, and all of the usual things that a program optimizer does, like a Haskell compiler or whatever, removing unused variables, dealing with Taylor recursion and recursive functions, all that stuff. So all these things are things that the Morel system could potentially do. And yeah, this general area is something I've already started investigating in Calcite, and Morel under the covers uses the Calcite engine under this general category of multi-query optimization. So optimizations that are possible if you look at several queries or DML statements all at the same time, that are not possible when you just look at them individually. And this, this could have real world consequences in just reducing people's spend on, their data engineering jobs.
Yeah, because if you do like the delta, like the except after the fact in SQL, right? Since the engine have no context of how it was produced, that you redo the compare, so it's a very expensive query. And if you want to do it in the same query, then your query becomes way more complex, right? Because you need to add a column to track whether you changed it or not. If you wanted to do keep track of what changed, what didn't change, you would have to add more columns to keep track of what you changed and make sure your logic is in sync, and then filter it out in multiple ways. It makes things more complicated. Than here, it's kind of nice and elegant and short.
Yeah, thank you. All right, so we're almost at the end here, but I wanted to look at some other query paradigms, beyond relational, and see how Morel can start addressing those. So one example is, I guess you could call this a graph query or a deductive query example. So we're interested in, you've got, let's say, the family tree of a bunch of elves, Elrond and Arwen and so forth. And if you represent them as a SQL table, you record, each elf person and their parent. Now you've basically created a graph. relationships between these individuals. And if we want to compute the transitive closure, a deductive language like Datalog is extremely good at it. So in Datalog, you actually define what are called facts. So a fact is, in Datalog, a fact is really like a record in a database, a thing that is true, right? It is true that, for example, Arundel is the parent of Elrond, right? So there are 4 rows in this database, there are 4 facts. And then I can run a query, I can run is parent, I can say what's the value of X such that Elrond is the parent of X. And Datalog is able to solve that problem, working backwards. And in fact, it's using relational algebra or relational calculus. It's just a different interface to it. In Morel, you kind of use the more traditional SQL way of doing it, and you use a where clause, and it produces the same answer. But when it comes to doing transitive closure, Datalog definitely has a superior way of expressing the query. So in SQL, or in recent versions of SQL, you can use this with recursive that can basically union together. You define the view ancestors, unioning parents with ancestors, and with recursive SQL computes the fixed point. So I can say what are all the ancestors of Arwen, and it says Elrond, who is Arwen's father, and Arundel, who's Arwen's grandfather. But it's, as you can see, it's rather verbose, and compare it to the Datalog solution on the right. I can simply define, I can say some X is an ancestor of Y if they're the parent of Y, or X is the parent of some Z, and Z is an ancestor of Y. So we've expressed that same recursive quality, but just much more concisely. And Datalog is able to work backwards from the solution and produce the answer. So when I tried to code something like the with recursive in Morel, I got a Stack Overflow error. And when you kind of look closely at it, it's kind of obvious why. The ancestors function is defined as, all of the parents union with the parents joined to the ancestors. So the ancestors function is just calling itself recursively, and it's calling itself with the same arguments, no arguments, right? So obviously that's going to produce a Stack Overflow error because it hasn't made any progress before it calls the ancestors function again. And I think the with recursive syntax in SQL is basically a bit of a con.
Yeah,
yeah.
I've used it, right? It's actually iterative, right? The way it works is creates a temporary table, right?
Yeah.
A temp table. It does the join, and it keeps joining against the temp table, right? So as soon as you're not adding any rows to it, then it stops, right?
Yep.
Because the table has now changed. So it keeps track. So it's with recursive, but it's actually only doing, I guess, tail recursion, right? You can always turn it into an iteration.
Yeah.
Against that one temp table.
Yeah, and I think with recursive, basically it's a way of presenting a query in this particular pattern. So SQL can go, aha, they want to do transitive closure, and then it, does its transitive closure algorithm.
Yes.
That's much more limited than what Datalog is doing, where you are literally defining, the deductive steps, and it's solving those deductive steps.
Yeah, I guess in Datalog you can probably have multiple recursion, right? It's kind of like exponential kind of exploration. When in the with recursive, I'm pretty sure you cannot, right? Like this kind of, it just keeps rejoining at this temp table, right? So you have like one. I think basically it has to be tail recursion.
Yep.
Kind of thing for this to work.
So the innovation here was, I just realized that Datalog is doing it right, and SQL's doing it wrong. SQL is trying to do it using relational algebra, which means it's like relational algebra is like baking a cake, where you start off with the ingredients and then you kind of mix the flour and the butter together and you sift it, right? So you start off with the ingredients, you do a sequence of steps, whereas data log is the opposite. You start off with the end result, you say what you want, what a solution will look like, and then it goes and tries and, backwards finds the right solution. So I decided to add this into Morel. So here's the Morel doing it in the forwards way. I can say define clerks as clerks where job, employees where job is clerk. In the backwards relation, I actually define a predicate, a Boolean function that says, is this employee a clerk? And so you'll notice in kind of from E on the right-hand side, I'm actually not saying what E is in. I'm not saying what collection E is iterating over. I'm just saying, I'm not saying where E is coming from. I'm just saying that E must be a clerk. And it can work backwards because it knows where all the set of all clerks are. It can work backwards and solve that equation for me. So the innovation here is this idea of an unbounded variable from E without saying what it is in. And these things work. If I just said from E and didn't specify any other conditions on it, it would be an invalid query because there's not enough to go on. But you can think of it as iterating over all possible values of the type. But the query is only going to be valid if there's enough constraints later on in the query that allow me to narrow down to the set of employees or whatever to a finite set. But it's still an easier way, well, not for this query particularly, but for deductive queries, it's just an easier way of framing the problem. So let's now look at how we do this in a deductive query. So in Morel, we can define a function isAncestor. So rather than defining an ancestors function that returns a set, isAncestor just says, given two variables, x and z, tell me whether x is an ancestor of z. And we've got a little query that will allow us to figure out whether x is an ancestor of z. And now we can just use this in a query. We can just say from A, where is ancestor A, comma Arwen. So now, A is an unbounded variable, but it's able to solve the equation. And you can see it's doing the same graph deduction that Datalog was doing. It's a little more verbose than Datalog, but still pretty good. It's able to work backwards from the solution. So this idea of unbounded variables and relations, I'm very excited because it allows a lot of forms of kind of logical programming, deductive programming, graph programming that are just not possible or incredibly verbose in a relational algebra language like SQL.
Yeah, I think in SQL there are two problems. One is this, like the with recursive, which you have to do things a certain way, right? And it's very verbal. And second is, it's interesting that you give the relations to the database, right? You define foreign keys or things like that. So knows that an ID is pointing to another table. But when you follow those links in SQL, you have to every time say join on this equal that, right?
Yeah.
And you always have to specify it. So it becomes very verbose when I'd like to be able to follow those links without having to tell SQL again that this is how you follow them.
Yeah.
In every query, right? Which I think like graph languages kind of take advantage of that. Makes it a lot easier to do transitive closure. It's just like keep following this link until you find this, right?
Yep.
And turn the set of all the things you found. Which is in SQL, it becomes very verbose. If you have a normalized schema and you keep following the links between the things, you end up with queries that are pretty long, and you had to define end conditions and things like that. Makes it difficult.
Yeah, and related to that, I mean, I would like to be able to define views with those relationships built into the view. So the stored data is still the same, but you can define a view which has, the set of dependents of each employee and the set of orders that that employee has, has placed. The view could basically define all of these different optional directions. And of course, you define it as a function that returns some complex data set, but any parts of that view you're not using won't actually be executed in the query because the optimizer is aggressively pruning stuff away that isn't needed. So that is a kind of way of having it both ways, keeping the data on disk nice and simple, but providing these very rich views so that people can, access all of the parts of their data model if they want to, but with no runtime cost if they don't.
And it's very composable too, right? Like you don't have to, like in SQL, you define views, they tie to tables, right? They look like tables, but here they are functions, so you can recombine them and have reusable logic to follow certain relations and so on in different ways, right? I think that's pretty nice solution.
Yeah, I mean, just the fact that you can have, when you call a function, obviously you can pass parameters to it. And the parameter could be, like a salary threshold of the employees table, or it could be even a predicate, like, a predicate which says which employees are interesting. So using functions to define views has a lot of interesting possibilities. So here's another thing you can do, which is again, you might not think of this as a query problem, but if I'm interested in, I'm running some kind of baking business and I'm trying to figure out how many cakes I can make with the ingredients I have available, right? And I have two products, a banana cake and a chocolate cake, that have different prices and use different ingredients. By the way, don't try and make these recipes at home. These recipes are not edible cakes, but they are just useful for the sake of example. So I'm interested in what combination of cakes should I make in order to maximize, my profit from the ingredients that I have. Doesn't sound like a query at all, but using this new idea of these unbounded variables, I can express it as it is kind of a mathematical optimization problem. And this is the query that I can write, and this actually works. So I can define these variables B and C, which is B is the number of banana cakes I make, and C is the number of chocolate cakes I make. And these various conditions, like I have, I can't exceed, I can't use, more than the flour that I use cannot, the combination of flour used by the two recipes cannot exceed the amount of flour I have on hand, right? And so, and likewise. And then I calculate the profit, and effectively, when I execute this query, it's going to iterate over all possible values of B and C. And then it's going to calculate the profit for each of those. And if I sort them descending, I will find the optimal value, which it turns out is 29 banana cakes and 14 coffee cakes. Chocolate cakes. So, and this is an existing field called constraint programming. But using this syntax, you can see kind of we're iterating over a relation of all the possible values of B and C. I think we've brought it into the under the umbrella of relational processing, and it introduces this possibility of hybrid queries where you could have, let's say, a combination of mathematical optimization, but also joining to some, relations on disk. So yeah, the overall goal here is to make database programming more like using a modern programming language. There are many nice things about modern programming languages, like a type system. If it compiles, it probably works, right? Also, the type system gives us this ability to do refactoring and auto-completion. So I can rename, tables or rename columns or whatever, and it just works. We like Git and this idea that, you and I could be working on features, and if I finish first, I commit my branch before you do, But nevertheless, the main line will stay working because each of us has to, execute execute the test suite, and rebase or merge on top of what the previous person has done. So we like that. That isn't what happens in the database, right? If the database administrator decides they're going to add a column to a table, everyone sees that new column immediately, right? And if it breaks the application, it breaks the application. Databases really don't fit into the way modern people do programming. So I'm trying to solve some of those problems. Databases, certainly it's a complicated problem in that there's two different kinds of changes happening in databases at the same time. So the schema is changing. So you might create the employees table, and later on you change the type of the hire date column, and then you add an extra rating column. Meanwhile, applications are inserting data and reading data. And these things are all happening in parallel. So you might have one particular application that is seeing the latest version of the schema. So it's seeing 5 columns, including the rating column. But it's looking at the data set as it was 2 hours ago, right, when there's only 900 rows. Meanwhile, another application is still working on an older version of the schema, but it's actually it's up to date. So this is certainly a hard problem of how you support these applications. But my idea, and this is just a sketch of an idea, it's definitely not fully formed. My idea is to say, let's just let's pretend the database is a module. And therefore, if I'm writing an application that wants version 3 of the schema, or version 2 of the schema, then I depend on a type for the employees table that looks like version 2. If the database is actually version 3 behind the scenes, then the system, I guess the Morel runtime system, is going to create shims a shim is basically a view that makes my employees table look like the way I want it to, I expect it to. And this is definitely early stage. I haven't solved all the problems, but the basic idea is my application, I can upgrade my database schema to a later version when it's convenient with me and my application development team, not when the DBA decides to add that column to the database. And I think the shims require obviously some considerable magic to make them work, but I think they're possible. And it seems like this is a nice world to be living in, if we can make it happen. And what's making it happen is the fact that database views are implemented using these functions, and then we have a strong type system, so I can represent the type of the employees table, by a record type. But my application and your application are actually going to see just different types because we have different versions of the schema. So yeah, that's all I have really. My conclusion, what I said, one of the goals was to kind of broaden out the space of data from just dealing with transaction processing and search into this broader set of problems, including constraint programming, arithmetic optimization, general purpose programming, in addition to doing all of the things that we currently do with SQL. And yeah, that's my last slide. So any questions or closing thoughts, Julian?
So you said a couple of times when we started Morel and so on. So could you tell us a little bit about how it all started and who's we and how it's evolving now?
Yeah, so we is mostly me. This has been Google has a thing called a 20% project, where, or at least had, back in the day, where you could spend one day a week. Well, I call this a 28% project. I've been working on this kind of weekends for I don't know, 3 or 4 years, because I think it's such an elegant idea. Like my day job is implementing SQL query optimizers, but I've been working on this for a while, just saying, well, what if we integrate query language with functional programming language? So I left Google, let me see, beginning of March, so 6 weeks ago now, I guess almost 2 months now, and I've been working on Morel full time. And so, you know, the rate of implementing features has picked up. So we should start seeing some, and I am really looking for people to use this, people to work on this with me, you know, contributions welcome, as they say. Contributions including just log bugs about stuff that doesn't work for you or stuff that doesn't make sense. So I'm, you know, having quit my job at Google, I want to make this thing successful, and I'm starting to spread the word.
Nice. And you said it can work on multiple backends. What backends does it support today to run it?
Yeah, so it can run in 2 modes. There's kind of regular local mode where everything gets, you know, all the data gets loaded into the client and the processing happens in the client. There's also a hybrid mode where it takes these expressions, these queries, and converts them to calcite relational algebra. And assuming it can do that, then we can use calcite's existing query optimizer to optimize this relational algebra, but also send it to any supported calcite adapter. So in particular, if the data is coming from JDBC, you can use calcite's JDBC adapter and convert that relational algebra to SQL. So working in that mode, obviously calcite is kind of the, you know, the secret sauce making it work. But if you're using Morel in that mode, when you write a Morel program, that Morel program would be executed on your backend database or backend databases by generating SQL. Now, there's a kind of a chicken and egg problem here, which is what happens if your Morel program goes beyond relational algebra, goes beyond SQL. You know, that's a problem that really only time can solve. But what I hope is that when people see, when these, you know, people making these engines see what can be done with extended relational algebra, perhaps extending the, you know, with recursive syntax, then, you know, they will start adding extra capabilities to these engines, because engines such as, you know, Spark and BigQuery are incredibly powerful. And I think it's a shame they're only being used for relational programs right now. I think it, you know, there's a real possibility for them doing other forms of data processing, because they're certainly capable of these things. In the meantime, Morel is going to, you know, do its best to convert these programs into whatever gnarly SQL needs to be generated to you know, to make the thing work.
You could generate a Spark program, right? Like that. The thing. Like Spark in general would be able to run those, right?
Yep.
And you need, like, generic SQL, you need to generate UDFs for certain things, right? Which, depending on the database, is not, you cannot just like make that part of your query. But in Spark, you should be able to do things. You know, should be interesting.
So that's the plan. As we kind of launch Morel and it becomes successful and we start looking for a commercial story, then, you know, supporting, we will pick 1 or 2 of these backends and, you know, make Morel work on these backends. But, you know, which backends we choose really depends on which workload people think is, you know, Morel is best suited for. I happen to think that, you know, data engineering problems like, you know, the DML example, I think that's a pretty good thing that Morel could solve. But well, you tell me. So yeah, give it a try. As it says on the screen, give it a try. You can go to GitHub, Git clone the hydromatic Morel repository, and provided you have some version of Java installed, you should be running Morel command line in under a minute. So yeah, give it a try.
I do have some version of Java installed.
I hope so.
Yeah.
And you know, although this current version of Morel is defined in terms of the JVM, I am designing it as a language, and you know, Java is okay. It's not the most efficient language out there. I hope that if Morel is successful, you know, within a couple of years, there will be an implementation of Morel in Rust, for example, and that the language will still look the same. So in the same way as when you're using SQL, you can't tell what language the engine is written in. My hope is that Morel will become a language that has implementations in various languages, and the users just won't know and won't care what the implementation language is.
Yeah, you showed us an Antler grammar or something, right? So
yeah, exactly.
So that can be implemented. Yeah, I mean, if you want to go with the cool kids today, you have to write it in Rust, right?
Yep. Yeah. Okay. Well, thank you. Thank you for the smart questions, and yeah, maybe I can do the same for you sometime with be a podcast host for your latest presentation.
Yeah, maybe this is the beginning of a long string of presentations like this.
That would be awesome. Yeah.
Cool. Thank you very much, Julian.
Thank you.
And hit subscribe. No, I'm just kidding. I don't know.
Punch that subscribe button.
Yeah, punch the subscribe button. And have a great rest of your day. I'm looking forward to our next chat.
Awesome. Thanks.
Bye-bye.